Welcome to the Deep Dive Lab. So, have you ever seen one of those, cutting-edge robots doing something just incredible, like a perfect backflip or navigating a chaotic construction site?
Oh yeah, the stuff you see online, it's amazing.
It is, and you look at these machines and you think, okay, we've basically conquered robotics. But if you watch them really closely, they all share this one kind of subtle, almost unsettling limitation.
It's that uncanny valley of touch. They can run, they can jump, but they don't flinch.
Exactly. We've built these hyper-advanced humanoids, right? Robots that are supposed to become household assistants or medical aids.
Things meant for close physical interaction.
And yet, they are fundamentally oblivious to harm. I mean, if you twist its arm too hard or poke it with something sharp, its main brain just registers, what, a tiny data fluctuation?
A blip on a screen, it doesn't pull away, it doesn't react. And that lack of self-preservation, well, it's a huge obstacle.
It feels like a safety issue.
It is. For a machine to safely integrate into our lives, it needs to understand when it's being damaged, not just for its own sake, but for ours. I mean, imagine a coworker who can't tell the difference between a high five and a hammer blow.
Yeah, that's inherently unsafe. Unpredictable.
And the tech we've been using, these electronic skins or e-skins, they're just so inefficient.
They're basically passive, right? Like a big, fuzzy touch screen wrapped around the robot.
Totally. They rely on these super complex centralized wiring grids, we call them M by N grids, to report every single touch point back to a distant central brain.
So they're just constantly sending streams of raw analog data.
A flood of information. Think of
Yeah.
it like trying to run an entire city's communication system by having one single operator take every single call. It's overwhelming, and the wiring becomes a nightmare. The bigger the robot, the worse that spaghetti problem gets.
Okay, let's unpack this. Because the deep dive we have for you today, it isn't about some small improvement. We're talking about a total architectural overhaul.
A complete redesign.
We are looking at a revolutionary new concept. A robotic skin that doesn't just sense touch, it actively detects pain and injury. And crucially, it triggers localized protective reflexes that bypass the main brain altogether.
This is really foundational stuff. It's all based on a research article. A neuromorphic robotic electronic skin with active pain and injury perception, which was just published in PNA, that's the Proceedings of the National Academy of Sciences, in December 2025.
And the work here was spearheaded by Yu Gao, Jianpeng Zhang, Hua Zhang, and their whole multidisciplinary team. They're from multiple institutions, including the Department of Biomedical Engineering at the City University of Hong Kong.
Their mission was basically to ditch that old passive system and move into what you might call true bionics. They've developed the neuromorphic robotic e-skin, or NRE skin, and, well, this could be the key to making the next generation of robots actually safe and self-aware.
So let's start with the architecture. If the old e-skins were just passive touchscreens, this NRE skin is trying to be a sensory organ, like real skin. How do they pull that off?
The key is that word, neuromorphic.
Yeah.
It means it's designed to mimic the nervous system.
Okay.
Unlike a passive sensor, our own skin's nerve endings, they actively generate these really efficient electrical signals pulse trains to encode everything.
Yeah.
Where the touch is, what kind it is, how intense it is.
So the intelligence is distributed, not all in one place.
Exactly. And the NRE skin literally mirrors that, right down to its layers.
It has layers.
It does. A four-layer design, just like our anatomy. On the outside, you have a protective layer, sort of like the stratum corneum in our skin.
Okay, the dead cells.
Right. And beneath that is the sensor layer, which is like the epidermis, with the actual pressure sensors. But the really critical part is the third layer, the circuit layer. That mimics our dermis, and that's where all the signal processing happens.
Ah, so instead of just sending raw data down a wire for the main brain to sort out, the NRE skin processes the touch right there at the site of impact.
That's edge processing right there. And what's so ingenious is the functional shift. The skin doesn't wait to be asked for data. It's event-driven. It converts pressure into those neural-like electrical pulses.
How does that work?
It's a physical property. The harder you push, the lower the electrical resistance in the sensor becomes, which directly translates into a higher frequency of pulses.
Got it. So instead of sending a continuous high-volume signal like leaving a mic open 24/7, it only sends these little bursts of digital Morse code when something actually happens.
Which is vastly more efficient for energy, for processing power, for everything.
Yeah.
It's the difference between a clunky old mainframe and a modern smartphone. This active hierarchical structure. It just slashes the need for all that spaghetti wiring.
It changes the scale of what's possible. You could actually cover an entire robot.
You could.
Okay, so moving past that basic structure, here's where it gets really interesting. Let's talk about hierarchical encoding. This is how the NRE skin manages this massive data compression. We're talking about an 8x8 sensor array that's 64 distinct locations.
Right.
But they funnel all that information down a single channel. How in the world do they encode the precise location into the pulse itself?
This is honestly the wow moment in the paper. They perform what's called progressive dimensionality reduction by embedding the location data into the characteristics of the signal itself.
Wait, so instead of sending 64 different messages down 64 wires...
You send one single message that has its own built-in ID tag. The central processor doesn't need to trace which wire the signal came from. It just has to listen to the qualities of that one pulse.
And what are those qualities?
The NRE skin determines location based on 3 distinct encoded features of that single pulse train: its overall shape, its physical width, and its final amplitude.
That is absolutely wild. Okay, let's break that down because it's easy to just gloss over how complex that is. How does it use shape?
Think of it like filtering radio frequencies.
Yeah.
The highest or coarsest level of localization is the pulse shape. The researchers tuned a circuit component, a shaping capacitor, to divide the whole 8x8 skin into 4 broad quadrants.
Okay, 4 big areas.
And each of those areas generates a pulse with a uniquely identifiable shape. One might be sharp-edged, another might have a more gradual, rounded profile. So if the robot detects a sharp pulse, it knows instantly the touch happened in the top left quadrant, for example.
It gives you a really fast general idea of where it was touched, and then it refines that with pulse width.
Correct. The next layer of detail is controlled by a resistor that determines the pulse width. Each of those 4 quadrants is then subdivided into 4 smaller sections.
Like a 2x2 block of pixels.
Exactly. And each of those sections gets its own distinct pulse duration. One might be narrow, the next might be a little wider, so now the system knows the quadrant and the section.
And finally, the finest level must be the pulse amplitude. That's what singles out the exact spot.
Yes, that's the last step. Using a feedback resistor in the circuit, they make sure the 4 individual pixels within that 2x2 block each generate a unique amplitude, from low to high. So by checking the shape, then the width, and then the amplitude, the system pinpoints which of the 64 pixels was touched.
And how accurate is that?
The researchers showed that a machine learning decoder can read that signature with 99% accuracy.
Wow. So the practical implication here is that the system can do this rapid, fuzzy localization. It knows roughly where it was touched just from the shape.
Prioritizing speed over precision. Exactly. When survival is on the line.
Which brings us to the function that really makes this system unique: the protective response, active pain sensing, and the local reflex.
This is the crucial safety feature. The inspiration here is the biological reflex arc, that lightning-fast, unconscious connection that lets you pull your hand off a hot stove before your brain even fully registers the pain.
Speed is everything.
It is. So they had to engineer a circuit that could bypass the robot's central brain.
How did they do that?
They built a dedicated pain evaluation center. Now, because incoming pulses have different signatures, they first had to be standardized. They're made uniform so the pain measurement is accurate.
Right, you need a uniform measuring stick.
Exactly. These unified pulses are then accumulated in a signal cache. And pain is triggered when the electrical charge in that cache crosses a specific threshold. The researchers set this threshold to correspond to an external pressure of about 360 kilopascals, or kPa.
And just for context, what does 360 kPa feel like?
It's a bit higher than the average human pain threshold. Think of like a forceful grab or a pretty strong punch. It's the point where the robot decides this isn't just a touch anymore, it's a threat.
And when it crosses that line?
When that threshold is breached, the system generates a high-amplitude signal. Because this signal is electrically way stronger than a regular tactile signal, it acts as a high-priority interrupt.
An override.
A total override. It directly activates the local motor control center. In their demo, it was a servo motor in the wrist, and triggers an immediate protective action, like yanking the hand away.
So that's the engineered reflex arc in action. No waiting for the main processor to decide if the danger is real. But I mean, pain is subjective for us. Is that threshold fixed for the robot?
That's a great question, and it speaks to how sophisticated the design is. The pain sensitivity is fully tunable.
Really?
Oh yeah. By adjusting the internal timing circuits, they showed they could set a low pain threshold, as sensitive as 205 kPa or a high one, up to 502 kPa.
That means you could program the robot's delicate hands to be super sensitive, like a surgeon's, but then program its robust back or chest to be less sensitive, so it doesn't overreact to a casual bump in a busy room.
It allows the robot to adapt its self-preservation instinct based on its role and its physical parts.
Okay, so beyond pain, they also had to tackle durability. This skin can't heal itself like ours can, so how does the NRE skin know when it's been, cut?
They built in this really ingenious self-check system. Think of it like a constant low-level heartbeat.
A heartbeat.
Yeah. The electrode circuit is designed to generate a periodic live pulse every minute or two when the skin is intact and undamaged. It's just a circuit saying, hey, I'm here, I'm fine, all systems nominal.
So if that circuit gets cut,
The circuit breaks, and the live pulse stops in that precise area. Every sensor has a paired timer that resets whenever it gets a pulse, either from a touch or that internal live pulse. If that timer overflows after about 5 minutes of total silence,
the system knows something's wrong.
it registers a definitive injury and knows its exact location.
And since regeneration isn't an option, they also address the repair side of things. How do you replace it quickly?
They went with a modular design. It's almost like Lego or maybe armor plating. The layers are held together with a quick release system, like a magnetic interface.
That's smart.
So when an injury is localized, you can just peel off the damaged module and snap on a new one. The whole thing minimizes downtime. It's like robot dermatology, but with the speed of an F1 pit crew.
And they showed this all working on a small humanoid robot, right? What was the result?
It was really compelling. Under mild touch, the robot registered it and showed a positive expression, like a little smile. Under heavy but tolerable pressure, below that 360 kPa threshold, it showed a mild distressed expression. But the second the pressure crossed the pain limit, you saw this intense pained expression. And critically, the local reflex kicked in and the wrist motor violently pulled the arm away.
It showed the whole safety hierarchy in action.
Gentle touches registered, strong touches noted, but dangerous pressure triggers an immediate survival response.
So that brings us to the key takeaways from the research by Gao, Zhang, and their team. This NRE skin is a serious leap forward.
I'd say so. First, you have a massive gain in efficiency and scalability. By moving from that bulky centralized wiring to a neuromorphic system, where location is hidden in the shape, width, and amplitude of one pulse, they've just dramatically cut the complexity. Full-body sensory systems are suddenly viable.
Second, and this feels like the most vital part, is safety. They introduced an active pain detection system that mimics our own reflex arc. That gives you immediate localized protection, bypassing the central processor's lag time. It fundamentally changes how safe these robots can be around us.
And third, there's durability and maintenance. That self-checking live pulse for injuries, plus the modular quick-release design for fast repair. It means these complex systems can actually handle damage and be back online in minutes.
If you connect this to the bigger picture, this feels like the first real step toward robots that have a foundational sense of self-awareness. I mean, for a service robot to be a reliable partner, it can't just be a tool.
It'd have to understand harm. Now, the researchers did acknowledge it's not perfect yet. They found that in really complex scenarios, like very high pressure on multiple points at the exact same time, the pulses can sometimes overlap and confuse the location reading.
So future work will need to refine those encoding strategies.
Sounds like a fascinating problem for the next generation of engineers. But the core achievement engineering self-preservation is undeniable.
Which leads us directly to that philosophical question these things always bring up. If we can accurately engineer a functional sense of pain into a machine, letting it feel injury and react to protect itself, what ethical line does a service robot cross when it stops being just a tool and starts becoming a sophisticated, self-preserving entity?
The engineering problem might be getting solved, but the moral one is just beginning.
Indeed. Thanks for joining us in the Deep Dive Lab for this exploration into bionic skin. If you enjoyed this analysis and want to get well-informed quickly on the biggest breakthroughs, be sure to subscribe. We'll see you next time.